Most of the technology comes from the marine industry, from us building high-speed race boats, hydroplanes, international racing catamarans. The experience that we gained from the marine industry in that competitive environment is what taught us all about foils, composites. So the history of the wind turbine primarily comes from building competitive racing machines in the open ocean. Water is 850 times denser than air, and the vessels that we built have won multiple world championships around the world racing competitions, and the experience from building foils in that environment led us into building foils for vertical axis wind turbine. We looked at the environment that's out there and saw that everything was very antiquated. The turbine that we subsequently designed is a laminar flow lift-based foil versus a drag-based windmill that you usually see out in the wind farms around the planet. The foils are designed to actually fly in a circle. It's not a straight NASA foil section like you see on an airplane wing. They're designed to fly in the set specific geometry. The lift is generated by the airflow over the foil. It's not drag-based. That lift that's created by the airfoil creates an accelerated air mass that comes off the back of the foil, and because these foils are designed to fly in that set circumference, the laminar flow coming off the foil creates a very narrow band of accelerated air mass. So the next foils that come around and fly in that circle actually fly into this very specific accelerated air mass. So when the wind is, for example, only blowing 2 miles an hour, we already have 6 miles per hour of airflow over the foil. When the wind is blowing industry standard, which is 8 meters per second or 18 miles per hour, we have 198 miles of airflow over the foil. That 198 miles of airflow is all torque, and all that torque generates to more power, generates to more revenue, generates to more energy. So these foils are very unique. They're patented. It was very surprising even to us that we in 2020 got patents issued to us and published for aerodynamics. When we thought that 400 years ago nobody can get any more patents on aerodynamics, we got it in 2020. So a very unique foil. It's designed to fly in that circumference. The foils all feed on each other, creating a rotating air mass. True wind actually flows around the turbine once the laminar flow is established. We have no air mass cavitation and no noise. And when you look at the big windmills, you'll hear the thump, thump, thump. We're running completely silent. So from the center of the turbine out to the foils, the distance between each foil and all the geometry is very, very specific and very well defined for this rotor. The composite materials, of course, comes out of the marine industry. We were 10 times stronger than steel at 6% the weight. It's a closed molecule. I won't get too technical, but it's a closed molecule, so it doesn't oxidize. So acids and alkalines don't affect the materials at all. We can put the turbines in salt water behind volcanoes in a sulfuric environment with no effect on the composites. The fact that it's 10 times stronger than steel and 6% the weight allows us to build these massive big structures that are extremely light. The complete rotor of our wind turbine actually is further reduced by putting the whole turbine on magnetic bearings. So even when you see a very big rotor, you can take a tip of a pencil and push it with a tip of a pencil and it'll start spinning. So the wind regime that we can operate is from a barrier breadth of air to any wind regime. The foils are further designed so that on the bottom end of the foil, or where, as the pilot would know, where the flaps would be on an airplane, we actually have a hollow built into the foil so that when we reach a true wind speed of 125 miles an hour, that fast accelerated boundary layer that comes off a foil will start separating from the foil, and then when that boundary layer starts separating, it'll create an air brake for the other following foils to come into, so that the turbine can't overspeed. We've had our turbines running up in the Arctic in sustained 85 miles an hour of wind, gusting 142 miles per hour for 4 years. We had our very first turbine was installed in New York. It ran through Hurricane Sandy. We had another turbine up in San Francisco, north of the San Francisco airport. So our prototypes have been out there running in very low wind to extremely high wind regimes where no other turbine can even come close to operating. The net annual power production window for even our small turbines, because of this envelope, is way bigger than even some of the big windmills. On average, our turbine is 30% the size with 20 times more power output per turbine. The fact that we have a laminar flow with no drag behind the turbines means we can put our turbines very close together. So we have a power density per acre of 58 times, plus the fact that they're 20 times more efficient. So the ability to take these turbines and put them close together and give us a tremendous amount of power density per acre is completely different from what's out there in the industry today. The turbine is also designed to be modular. It's designed to fit into 40-foot containers. The implementation for using standard off-the-shelf trucks, standard off-the-shelf cranes, shipping them anywhere in the world and installing them within a week is totally unprecedented. These turbines have no metal in them, no gearboxes, no hydraulics, no oil. It's just a composite rotor sitting in a magnetic field. The generator is actually built into the composite. It's part of the unit. Saltwater and ocean storms and hurricanes can break over this thing all day long. It's not going to hurt the turbine. Sonia will play you guys the video so you can get a little bit more.
See what I mean? Give us a round of applause for the scientists. Okay, there's 2 ways for all you techie people to hang out with Oli. Number 1, good luck with that. Number 2, good luck with that.